In this video, we're going to do an example where we parameterize some surface and then use the surface area formula to compute out what the surface area of that actually is. So this problem reads, find the surface area of some plane, the plane that's described by z equal to minus x, that is inside the cylinder x squared plus y squared equal to 4. So before I do anything else, I always like to try to visualize what's going on. So the way I like to visualize this is, first of all, let me draw a generic plane here, maybe something like that. I'll treat this as the plane z equal to minus x, although I haven't bothered with any axes. And then I need to draw a cylinder as well. That's what x squared plus y squared equal to 4 is. It's an infinite cylinder. And so if I come along here and draw a cylinder like that, now if the plane was completely flat, the cylinder coming up would form a circle here. But because the plane is twisted, what results when you cut it by the cylinder is it creates an ellipse. So I'll try to sort of loosely sketch some sort of ellipse on here like this. So it's sort of an angled ellipse that might look a little bit like this. Okay, so hopefully we have an idea of what we're going on. And to be clear, the question is asking the surface area of the portion of the plane. So I only care about the cylinder in the sense that it's the thing that does the cutting. The surface area I'm computing is the surface area of that portion of the plane. So what I want to do now is come up with a parameterization for the plane. And because the boundary is going to be, well, a cylinder, I kind of want to use that, the geometry of what this boundary is, when it comes to expressing a parameterization for the plane. As in, if I didn't know anything about the boundary at all, well, I might not even care to come up with a parameterization. Z equal to minus x seems perfectly fine. I can imagine future integrals I might do would be perfectly fine. But because the region has a circular symmetry, it makes sense to try to parameterize that in the same way. So I'm going to parameterize it as follows. I'm going to say that my position function as a function of r and theta, so I'm going to use standard polar coordinates, is going to be written as, well, in the I hat component is r cosine of theta, in the j hat r sine of theta. And then what should I do for the z component? Well, z is minus x. X is r cos theta, and so that's minus r cosine of theta. And the really nice thing is, I know what my constraints are on my r values and on my theta values. Because it's the cylinder of radius 2, 4 is 2 squared, this means that for my r values, it's going between 0 and 2. And that for my theta values, it's one full circle, so theta is between 0 and 2 pi. Okay, so let's just move up now that I've sort of chosen my key data here. I'm actually more or less able to run out the computation. So let's first perhaps recall that the surface area is going to be a double integral of the magnitude of the cross product. So the cross product is r with respect to the first variable, which is going to be r cross r with respect to the second variable, which is going to be theta, dr d theta, and then r is going between 0 and 2, and theta is between 0 and 2 pi. This is the formula that we've derived in our previous videos. So the main thing, because I've already got the limits of integration, that was easy, the main thing is figuring out this integrand. So how can I do this? Well, let's do some computations. The partial derivative of r with respect to r, so I see an r in each place, this is just going to be cosine of theta, sine of theta, and minus cosine of theta. The derivative with respect to theta is going to be, well, the derivative of r cosine is going to be minus r sine of theta, r cosine of theta, and r sine of theta. Oh, I started writing cos. R sine of theta. Okay, so I've got those two things. Now I need to take the cross product. So I'll take r cross r theta. I always think it's funny saying r, but they do mean different things. Position vector, derivative with respect to the first parameter, that's labeled r. Nevertheless, it's a cross product, so I have to do some big determinant. I got my I hat component, my j hat component, and my k hat component. And I'll just copy and paste the two lines that I had. First the rr, and secondly the r theta. Okay, so hopefully this will be a straightforward computation, but let's see. So in the I hat, I'm going to have an r sine squared minus is a plus, r cos squared. Sine squared plus cos squared is 1, so I'm just going to multiply that by r. Excellent. Then I subtract off my j hat. Let's see what happens here. So I have a r cos theta sine theta minus a minus minus, three minuses, so it's a net minus an r cos theta sine theta. Oh, good, that cancels, that gives me just 0. And then plus a k hat, and this is going to be, looks like r cos squared minus minus a plus r sine squared again. So same story again, plus an r. Not so bad, really. Length of r cross r theta is square root of r squared plus 0 squared plus r squared. I'm taking the square of each of these different components. And so this looks like square root of 2r squared. And now I can write down my formula. So the arc length is that integral from 0 to 2 pi and 0 up to 2 of square root of 2r squared dr d theta. I do want to note one thing that can sometimes trick people. Sometimes people are tempted to put an r in there and add that in. This is not something you need to do. The temptation is that back in multivariable calculus, when you started with a double integral and converted that double integral into a polar integral, that the conversion of dx dy became r dr d theta. And so people want to write down an r when we've done this here. But that's not what we're doing here. Our whole formula was for a parameterized surface, and I've parameterized it in a particular way, and I'm just writing down what the parameter is. As in, this whole integral is occurring in the r theta space. It wasn't like we started in the xy space and then converted it. And as a result, you don't need to do that trick that was important when you were taking a Cartesian double integral and converting it to a polar integral. That's not what we're doing here. So there's no r, nevertheless we get this integrand. This is all straightforward, so the square root 2 is going to come out the front. Square root of r squared is just r, since r is always positive. This is, of course, is going to integrate into r squared divided by 2. So I'll write 0 to 2 pi, and then r squared over 2 from 0 up to 2 d theta. That integrand evaluates into 4 over 2, which is just 2. And then I'm integrating it from 0 to 2 pi, and so I'm going to get a 4 pi. So root 2, 4 pi, final answer. So what I thought was the most important part of this computation was the choice of the initial parameterization. And if I'd just given you the plane, you never would have thought to use this particular parameterization. But because it was a plane inside a region that has a sort of circular symmetry, it made sense to use the r and the theta as your parameters. And as you can see, it just sort of all evaluated out pretty nicely when we were doing that. If instead we tried to stick with x and y as your parameters, you'd get to the point of trying to write out the bounds on your double integral, and it would just be a big whole mess because it's just hard to describe circular regions in Cartesian coordinates.